All right, here we go. So dimensional analysis. This is a fancy name. It looks silly, but this is just the analysis of units. Looking, fancy name for converting a measurement or answer from one unit to another. So usually you have an equality, like 1 foot is 12 inches. And these are called conversion factors. Now, very important. If you remember this rule, this will make a lot more sense to you. When you write a conversion factor, can you see if a foot is equal to 12 inches, this is equal to 1, and this is also equal to 1. That's what I have written in red here. When calculating sig figs, which is the last thing we learned earlier, we're going to not count the numbers in the conversion factors. We'll assume that these have infinite sig figs. Because 1 foot is defined as exactly 12 inches. So usually these conversion factors we use are definitions, and when you have a definition, that means 1.0000 repeating infinitely is equal to 12.000 repeating infinitely. And for adding, subtracting, multiplying, dividing, that means those don't come into play when you're calculating sig figs. So if you are asked how many yards are in 5.28 inches, we would use two conversion factors, from inches to feet, and then from feet to yards. Hopefully you know that there's 3 feet in 1 yard. Now I've done this for you, but if you want to try to do this on your own because you remember, you can, but you don't need to do anything special here. So you always start a conversion with what you were given, the 5.28 inches right there. And in the next step of your conversion, you have to be able to cancel out whatever unit you started with. So notice the inches, we're just focusing on these first two sections here. So the inches have to cancel out. I don't put inches on top because then I would have inches times inches and not inches divided by inches. So now these inches cancel, and 12 inches is equal to 1 foot. Notice I've only multiplied this 5.28 inches by the number 1. So I haven't changed the actual quantity, I've just changed the units. So now I'm at foot, or feet, and I have to cancel out the feet, and I know 3 feet equal 1 yard, so I put the 3 feet on the bottom and the 1 yard on top. The feet cancel, and I'm left with yards. And I do 5.28 divided by 12 divided by 3. Students have trouble with their calculators here. You might want to come into class and have me work with this on this with you. Lots of different methods. Calculate the whole bottom, calculate the whole top. This one's pretty straightforward, but you'll see sometimes you will get the wrong answer and you'll wonder, what am I doing wrong? My calculator's not working, or Dr. Udell did something wrong. Sometimes it's me, but sometimes it's just the calculator. Now, we're only going to keep 3 sig figs because the initial number had 3 sig figs. The 5 and the 2 are measured, the 8 is estimated. Remember that last digit's always estimated. There were no leading zeros. So there we got 3 sig figs. We need to round this to 3 sig figs. So the answer will be 0.147 yards. Okay, try this on your own. Go ahead and pause the video. We're given all this information about Harry Potter's world. Pause it, and here's the answer. We need these two conversion factors. So we had 3.2 galleons, and we need to cancel the galleons. So galleons go on the bottom, and we can convert galleons to sickles right here. So galleons go to sickles, and we had 29 sickles in 1 galleon. And now we need to cancel out the sickles because we're trying to get to newts. We know 17 newts equals 1 sickle, so sickles go on the bottom in order to cancel them out. And there's 1 sickle in 17 newts, right? So I just multiplied by 1. That's all I'm doing, nothing fancy. And then I multiply 3.2 times 29 times 17 divided by 1. We get a big number, and we have to keep only, let's see, 2 sig figs. So I round this. Now notice I have these trailing zeros. These, I haven't really talked about this, but if no decimal showing, we're not going to count the zeros on the right side. Okay, so I'm pretty sure, sometimes I pause and I can't remember where I left off, but I'm pretty sure we had just finished this problem. This is 1600 because we had to round to 2 sig figs. And so this is the very first measured number, and so I'm only going to keep these 2 digits. You always keep the first measured number, or the first significant digit in the calculated answer, which would be this one, and I can only keep 1 more than this. Now this 1600 is ambiguous about whether it's 1, 2, 3, 4, or 1, 2, 3, or only 2 sig figs. When there's no decimal showing, those trailing zeros are ambiguous, so it's much better to write this in scientific notation to clarify how many sig figs you really are suggesting. This would be 1.6 times 10 to the third newts. And now we are no longer ambiguous. So, yeah. So your turn. Do this one. So you pause, and I'm about to show you the solutions, but pause. Don't just copy this down. Try to do it on your own, following the previous example. So here's the solution. We would start with our 140 newts or nuts. I don't know how they pronounce that, knuts. And we have our conversion, 17 knuts equals 1 sickle. So we have to cancel the knuts like this. So 70 knuts, 1 sickle, 29 sickles, 1 galleon. We get a number. And we have to round to 1, 2, 3, 4 sig figs. So we have to round this to 4 digits, 4 significant digits. Leading zeros never count, so this 0 does not count as significant. So the 2, the 8, and the 3 I keep. This digit I keep, I have to figure out whether it rounds up or stays the same. It rounds up because this is a 7. When you round 9 up, it makes 10. You add 1 to the 3, and you get 0.2840 galleons. Moving on, Chapter 2. We are into the atomic theory. And this is just, what is an atom? This was formulated in the very beginning of the 1800s, 1808, by John Dalton. All right, so elements are made of very small particles, and we call those particles atoms. Atoms of a single element are all identical, size, mass, and chemical properties. We learn later that the masses can actually be different for atoms of the same element. Compounds have at least 2 different elements. We learned that actually earlier in Chapter 1, but this was part of the atomic theory. And the ratio of atoms of any 2 elements in a compound is a whole integer or a simple fraction, like 3 to 5, 1 to 2. Well, 1 to 2 is a whole integer. A simple fraction would be like 2 to 3, or 3 to 8, or 3 to 5. And a chemical reaction separates, combines, or rearranges atoms, doesn't create or destroy atoms. That's the theory. Okay, law of definite proportions. This is an important law, and it states that if you have different samples of the same compound, the sample should always have the same ratio by mass of each element in the compound. This law in and of itself, it's not that the law is so important, but the law helped us understand a concept we will learn later, which is the mole concept. Let's do a problem, like what does this mean for us? It says if we have 2 samples, A and B are 2 different elements, and the formula is AB2. That means we have 2 atoms of B for every 1 atom of A in this compound. So we have 2 samples of the compound, and we know one sample has 12 grams of A and 32 grams of B, and the other has 18 grams of A. How many grams of B are in the other compound? Well, you have to have the same ratio by mass of each element, so the ratio of A to B in this sample of the compound must be exactly the same as the ratio of A to B in the other compound. That gives us this ratio right here. Here I'm doing B to A, so 32 grams B to 12 grams A must be X grams B to 18 grams of A. So we see the ratio of B to A must be the same in each sample of the compound, and you should be able to solve this yourself. You can pause or just watch when I put the answer up. There it is. The second compound must have 48 grams of B. So any time that you have a sample and you're told the masses of all the elements in the sample, if you have another sample, you can find the masses of, as long as you have the mass of one element in the sample, you can find the masses of the other elements in that sample by setting up these proportions. Okay, another law. Law of multiple proportions. Now this isn't about the same compound. It's saying if you have 2 elements, 2 or more elements, that can form more than one possible compound, suppose you could have AB2 or AB. An example would be CO2 and CO. This would be carbon dioxide and carbon monoxide. The mass of one element that combines with a fixed mass of the other element must be a ratio of small whole numbers. We're not going to do problems involving this. It's saying if in CO2 I have 12 grams of carbon and 32 grams of O, and I'm told I have 12 grams of carbon in the other compound, the ratio of oxygen in this compound to this compound must be a ratio of small whole numbers. It's hard to do problems like this. It's just important to know the law. Conservation of mass, we cannot create or destroy mass. And this leads us to know that when we have a chemical reaction, the mass of the reactants must equal the mass of the products. Continuing on. Atomic structure. We've learned through a various number of experiments that atoms are made of protons, neutrons, and electrons. We're not going to worry about smaller particles. That would be for physics. And these particles have charges and masses, or no charge. So the electron has a symbol of E minus. This is the actual mass of an electron. Here's the charge. And in charge units, we just say an electron has a -1 charge. Coulombs are a different unit. So there's 1 charge unit for every 1.6022 times 10 to the -19th coulombs. You won't need to know that conversion. I would give it to you if we were doing it in a problem. You should recognize the proton has a charge of +1. The neutron has a charge of 0. Neutron, neutral. Notice the charge, oops, this should be positive, not negative. The proton and the electron have equal and opposite charges. So we say as far as charge units are concerned, it's -1 +1. And then looking at these masses, notice the proton and neutron have about the same mass. In fact, the difference in their mass is equal to approximately the mass of 1 electron. If we add these two together, we get very close to this. Not quite. It's a little more complicated than that. But a proton and an electron together make up a neutron. It's very strange. But don't worry about that. That's nuclear chemistry. We are not going to get into that. The key things here are recognizing the charge differences between all three, and then that these two each have a much larger mass than an electron. That leads to this next thing. I just talked about these interesting things to note. Mass number. When you calculate the mass number, not the total mass, but the mass number, we add protons and neutrons because the mass of this electron is so negligible compared to the proton and neutron. There is still that mass of the electron present, but the mass number is a whole number, and so these are clearly not whole numbers. It's just we talk about mass number, total number of protons plus neutrons. Okay, lots of information coming up right here. So atomic number, it's the whole number on a periodic table. Now you have a periodic table here. So these whole numbers that you see here, those are atomic numbers. When you look at any periodic table, most of them also have atomic masses. Sometimes those are whole numbers, sometimes they're numbers with decimals. Those are not the mass number. You might want to write that down, that atomic mass does not equal mass number. That mass number doesn't equal atomic mass. It's important. Okay, so let's get back to here. Atomic number is the whole number on the periodic table. It equals the number of protons for any element. So your protons identify who you are. You might want to write that down. Protons identify who you are. And this Z right here is the atomic number. It's your number of protons. Right there I wrote it. Z is your atomic number. It's your number of protons. A, when you write a symbol like this is called an isotopic symbol. This A up here, that's your mass number. Very strange because atomic number starts with the letter A, but we use Z because Z represents charge. And then mass number uses the symbol A, even though atomic number starts with A. So it is a bit confusing, but every book uses this notation. So you have to know this notation. So we have these symbols like this. X is your element, so that would be AT or I or BR or CL. It would be the symbol for the element. Now isotope, we'll talk about isotopes a lot. And an isotope is a specific atom with a specific number of neutrons. And atoms of the same element that have different numbers of neutrons are called isotopes of one another. We write them like this. So when we change the number of neutrons, do we change the atomic number if it's the same element? No. But if we change neutrons, do we change the mass number? Yes, because the mass number right here, A right here, is protons plus neutrons. If I change the neutrons, I change A. If I change neutrons, I don't change protons, so I do not change Z. This number down here stays the same. The number on top changes. You might notice I've repeated that about 10 times now. It's important to know. All right, let's do some problems. So if I write 3,1 hydrogen, it's actually called tritium. You don't need to know that. So tritium, the number 1 down here is how many protons. The number up here is protons plus neutrons. So looking at the difference there, 3 minus 1 is 2 neutrons. That's an isotope of hydrogen with 2 neutrons. Not so hard to see. And sometimes isotopes are written in this form, hydrogen dash the number 3. That says we're dealing with an atom of hydrogen, and this particular atom is an isotope with 3 minus 1, because hydrogen has 1 proton, 3 minus 1, 2 neutrons. When you write this format, the number here is your mass number, A. Okay? So you should be able to go from an isotope written like this or an isotope written like this to tell me what the element is, how many protons there are, how many neutrons there are. You should be given the element, tells you Z. If you're given the mass number, you know, then you can calculate how many neutrons there are. So write the isotope representation for each of the following. Let's see, do I have the, oops, I have the answers there already. So pause this. I'm about to show you the answers. Okay, how did I get this? Sulfur, we look it up on the periodic table. We find out its atomic number 16. Sulfur, atomic number 16. That's how many protons we have, and that goes at the bottom. 16 and 18, because there's 18 neutrons, gives us a total mass number of 34. And we're done. Element 24, well, we look it up. We see element 24 is chromium, so that gives us the X. The 24 goes on the bottom, and it's chromium. 24 plus 27 is 51. Here's our isotope. Okay, mass number 68, 37 neutrons. So we know 68 goes on top. And to get the protons now, we have to subtract 37 from 68. Gives us 31 protons. Then we have to look it up on the periodic table. 31 protons is gallium. There we go. All right. Moving on, you should now be able to figure out these, how to write these, given this information, and you should be able to do this backwards. If I ask for neutrons, when I've given you this, you should be able to figure out that there are 37 neutrons. Okay, so when we are looking at a row in the periodic table, that is called a period. A column in the periodic table is called a group or family. You might want to mark this up. Now, I know myself, I get confused between rows and columns, and I always have to stop and think for a moment. I don't know if you're like this or not, but you know, don't just quick go ahead, oh, period, okay, I know this is a period. No, periods are rows. So you have to always think row is a period, column is a group or family. Mendeleev put together our current form, is basically our current format. It's very, very close to this. There's a slight change. I'm trying to remember. I think it's somewhere in this area. There's 2 elements that are switched from Mendeleev's original version of the periodic table. So it's back in 1869. We'll learn much later in chapter 7 how he figured out his particular orientation of where elements should go. It's actually amazingly cool. Okay, we have all these colors in here marking different, delineating different families. So here's a family that is alkaline metals. This family is alkali metals. Do not confuse the two. They are different, alkali, alkaline. Transition metals, all of these in the middle. Rare earth elements, there's a couple more. The bottom two rows down here are rare earth elements, noble gases, halogens. Everything in yellow, those are semi-metals, or called metalloids. And there's some more information down here. There you go. You're going to be responsible for knowing all of those families I just mentioned. And you should also know that noble gases and halogens are also nonmetals, as well as these right here. Okay? Everything is organized by the periodic table. It's not that hard to remember things as long as you remember this. And by the way, if you draw a little ladder here, you will see, oops, start here and then go down, 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 down. The semi-metals pretty much touch that ladder. Everything that touches the ladder is a semi-metal except for aluminum. Okay. Metalloids. These have properties intermediate between metals and nonmetals. And also note, if you go across a period, a row, you go from metal, transition metal, semi-metal, non-metal. So we're transitioning from pure metal to a transition metal, semi-metal, non-metal. Every row does this. Metal, transition metal, these are actually post-transition metals, semi-metal, non-metals. And so there's a periodic way in which the elements change from metals to nonmetals. If you plot atomic number versus metal or nonmetal, or moving from metal to nonmetal, you'll see that you get something that goes like this. That was like a sine wave. You probably don't know what sine waves are yet. You will later. You don't have to memorize that. Okay, this is very important. You should highlight this. Chemicals within a family react chemically in similar ways to one another. Very important. So if you're told fluorine reacts with beryllium to form BeF2, then chlorine should also form BeCl2 or BeBr2. You don't have to know that fact. You just need to know if fluorine reacts a certain way with bromine in a certain ratio, chlorine should react in the same way. However, oxygen and beryllium react. Sulfur and beryllium should react similarly. Magnesium and sulfur should act similarly to beryllium and oxygen because these two are in the same family and these two are in the same family. So families react similarly to one another. Okay, molecules and ions. Molecule, at least two atoms held together by a covalent bond. When nonmetals combine, they make molecules. Ion, charged atom or group of atoms. Cations positive, anions negative. Mono means one. Monatomic ions have one atom. Poly, many. Polyatomic ions, two or more atoms. The names pretty much give you their definition. And ionic compounds usually made up of a metal and a nonmetal. So if we put together a metal and a nonmetal, we have an ionic compound. If we only have nonmetals together, two or more atoms in the same substance, we have a molecule. Molecules can be compounds or pure elements. Okay, electrons, identifying electrons. So, in an atom, all atoms are neutral, no charge. So protons and electrons would have to be equal. Cation, positive charge. So must have more positives. Which were the positives? The protons were positive. So if an ion is positive, it has more protons than electrons. If it's negative, if an ion is an anion or negative, you'd have more electrons. And the charge tells you how many more protons or electrons you have. So, N3 minus. This is negative. Nitrogen has, let's see, nitrogen, where did we go? We're over here. 7 protons with a charge of -3, 3 extra electrons. So 7 and 3, 10 electrons. see, did we get it right? 7 protons, -3, 10 total electrons. Typo. Okay, so sulfur with 18 electrons. Sulfur has 16 protons. If it has 18 electrons, electrons, remember, are negative. We have more electrons. 2 extra electrons, 16 protons, 18 electrons, 2 extra electrons gives us S2 minus, right there, S2 minus. Okay, you're going to write the missing number. Go ahead, pause this, and here come the answers. Okay. Molecular formula. It's a formula unit. When I say formula unit, I'm talking about the formula and one unit of whatever formula is written down. We can talk about molecules or formula units. When we have an ionic compound, we can't really call them molecules because they're ionic compounds. And so we would talk about formula units of ionic compounds. Don't worry, I'm not going to test you on any of that verbiage in terms of formula units versus molecule. Okay, you just need to know molecular formula is, it shows the exact number of atoms of each element in a compound. An empirical formula is the simplest. If there's a common factor, you divide the subscripts by the common factor. So here's an example. If I have ethane or propene, don't worry about those names, C2H4 versus C3H6. Now, do you see there's a common factor of 2 here? This could be simplified to CH2. This one right here, simpler formula, divide by 3 because there's a common factor of 3. The empirical formula for this, the empirical formula is the simplest, divide by 2. Empirical formula of this is CH2. Notice these both have the same empirical formula. Note that the empirical formula, CH2, does not tell us the actual molecule or formula unit. It's just saying the formula unit or molecule is some multiple of CH2. And we'll learn far more about this in the next chapter, and that's it. That wasn't it. I tricked you. One more thing. The formula for ionic compounds. You know, the book has it as formula of ionic compounds. I like formulas of ionic compounds. It just doesn't sound right the other way. Okay, cations. This is not misprinted. That is how you spell a cation. I mean, it's not misspelled. Okay, if you put a cation and an anion together to make a compound, you have no possible net charge on the compound. Compounds have to have 0 net charge, so the positives have to cancel. So if you put together O2 minus and Na plus, this is an oxide ion and a sodium ion. Well, the 1 plus and the 2 minus, do you see you need 2 of these to cancel the -2? So you'd have +2, -2, and that would add to 0. So this would be your formula. Now you're going to try the following. Okay, so here's all your things. You're going to pause in a minute, but I have a couple quick things to explain to you. D is tricky because you have a 3 and a 2, and how do you make +3 cancel with a -2? You have to think about least common multiples. What do you multiply this by to get a number that will equal this times something? Okay, another, just these two, we have these polyatomic ions, so I'll sort of do this one for you. If you have Mg2 plus, this whole OH has a -1. Oh, by the way, when you just see a negative without the number, it's -1. Or if you see a plus without a number, it's just +1. Okay, so here you should see that you need 2 of these because you have 2 negatives to cancel with a 2 plus. And the way you would write this is Mg parenthesis OH parenthesis 2. I can't write very well. That wasn't even the smartboard. That was just me using the smartboard tools, but using my little pointer to actually draw. See, it's hard to draw straight lines. Anyway, that would be the answer for E, and then you can try F on your own. And you can also just, I'm going to erase this, you know, do that as you're going through them. So do Mg with OH again, and pause this, do the problems, and then look. Okay, I'm about to show you the answers. Oh goodness. And here are the answers. Oops. There you go. Let me make sure I did these right. I think I did. Yeah. And this was the tricky one. You had to get a factor, least common multiple of 6. So you multiply this one by 2 and this one by 3. So now you have plus 6 and negative 6. It just gets tricky when you have a 3 and a 2. When you have a 1 and a 1 or a 1 and a 3, it's pretty easy. All right, now that's it for this chapter. For now. We'll do the next section at some later time.